Welcome back, Marauders. Video 3.7, Limiting Reactants. We'll talk about limiting reactants, and we'll also talk about percent yield in this video. So limiting reactants first. The limiting reactant is the reactant that determines how much of the product can actually be produced. A lot of times, if you know how much of each reactant you have, one of them is going to run out first, and that's going to limit the amount of product that you can make. The easiest way to do these is to determine, the easiest way to determine the limiting reactant is to do two stoichiometry problems. So just like we learned in the last video, we learned how to do basic stoichiometry starting with grams of reactant and going to grams of product. We're going to do that same process twice, see which one produces less, and that'll tell us which one the limiting reactant is. So the one that makes less is the limiting reactant. Here's an example. 4 wheels plus 1 board makes a skateboard. So pretend that's my chemical equation. And then I have 8 wheels. So 8 wheels is enough to make 2 skateboards. And I have 6 boards. That's enough to make 6 skateboards. But the wheels are going to run out first. You only have enough wheels to make 2 skateboards. Once those 2 skateboards are made, it doesn't matter how many extra boards you have, you can't make any additional skateboards. So if I had 8 wheels and 100 boards, I could still only make 2 skateboards. Kind of the same concept we're going to see in our stoichiometry questions. All right, so here's a question. We've got a balanced equation for nitrogen and hydrogen making ammonia. And it says, what mass of ammonia can be produced from a mixture of 100 grams of nitrogen and 50 grams of hydrogen? All right, so like I said earlier, the easiest way to do this, there's multiple ways of doing it, but the easiest way I think is to do 2 stoichiometry problems. So we'll start first with the 100 grams of nitrogen, and we'll go through and see how much that can make. And then completely separate from that, we'll take our 50 grams of hydrogen and go through the process and see how much of the product can be produced using that hydrogen. All right, so starting with the nitrogen, we're going to take the molar mass. Molar mass of nitrogen is 14. It's diatomic, it's N2, so we have to double it. So 28 grams of N2 for every 1 mole of N2. Second step, changing moles of what we have, the N2, that's going to go on the bottom, into what we're interested in. We're interested in how much ammonia can be produced. So moles of NH3 will go on top. The ratio between these 2 moles of ammonia for every 1 mole of nitrogen. And then we'll add up the molar mass of ammonia. So 14 for the nitrogen, plus 3 times 1 for the hydrogens, so that's 17 grams of NH3 for every 1 mole of NH3. And so with that nitrogen, we have enough nitrogen to make 121.4 grams of ammonia. Okay? We don't know if we'll actually be able to make that amount, because we don't know if our hydrogen is going to run out first or second. We don't know if that's the limiting reactant or the excess reactant. So let's do the same process with the 50 grams of hydrogen that we were starting with. So hydrogen's molar mass, it's diatomic, so 2 times 1 is 2 grams of hydrogen for every 1 mole of hydrogen. And then from the balanced equation, 3 moles of hydrogen are required to produce 2 moles of ammonia. And then changing it back into grams, same molar mass we had up here, 17 grams of ammonia for every 1 mole of ammonia. And so we'll do this on our calculators, and it gives us 283.3 grams of ammonia. So with the nitrogen, I can make 121 grams. With the hydrogen, I can make 283. Well, it doesn't matter how much I can make with the hydrogen, because as soon as the nitrogen runs out, the reaction stops. So this is how much I'll actually be able to make. This is kind of meaningless. Nitrogen is your limiting reactant, and hydrogen would be called my excess reactant. Okay, so it doesn't matter. The other thing to notice here, a lot of times people are tempted to think that, oh, since there's 50 grams of hydrogen and 100 grams of nitrogen, well, 50 is less than 100, so that must be your limiting reactant. Not always the case. You need to take into consideration what the molar mass of each substance is and what the mole ratio is in the balanced equation. So in this case, even though we had twice as much nitrogen, it ran out first and was limiting and was determining how much of the ammonia was able to be produced. A lot of times in these questions, you'll also be asked to figure out how much of the excess reactant remains. Okay, so my excess reactant was hydrogen, and we started with 50 grams of it. We want to know how much of that 50 grams is left over at the end. A couple different ways to solve these problems as well. The way I like to do it is to take my limiting reactant, the 100 grams of N2, and then I'm going to go through and see when all 100 grams of nitrogen is used, how much hydrogen is going to have to go along with it. Okay, so grams of nitrogen, let's change that to moles. 28 grams of N2 is the molar mass for every 1 mole of N2. And then I'm going to look at this ratio right here. 3 hydrogens, 3 moles of hydrogen are used every time 1 mole of nitrogen is used. And then the molar mass of hydrogen, 2 grams of hydrogen for every 1 mole of hydrogen. So I'm going to do that on my calculator. That's going to tell me that 21.4 grams of H2 are used in the same amount of time that all of my nitrogen is used up. All right, and so how much hydrogen is left? Well, we started with 50 grams at the start, and we used 21.4, so we'll just subtract, and we find that we have 28.6 grams of H2 left over. Second topic in this section is percent yield. So percent yield is something that we usually calculate after a lab. We usually do calculations and figure out how much of a product should be produced based on the calculations based on stoichiometry. But when we actually do it in a lab, we don't always get exactly as much as we predicted. So we often do a calculation called percent yield. It's pretty simple. You take the actual amount, so that was what you measured in the lab, and divide it by the theoretical, that's what you calculated it should be, and then multiply by 100 because it's a percentage, right? So it's what you got in the lab divided by what you calculated times 100, and that'll give you percent yield. It'll tell you how close the reaction was to the predicted calculated value. All right, so here's an example. Aluminum reacts with bromine and produces aluminum bromide. In a lab, 6 grams of aluminum react with excess bromine, and 50.3 grams of aluminum bromide are produced. What is the actual yield? What is the theoretical yield? And what is the percent yield? All right, so this wasn't a real lab. This just tells us what the actual yield was. So the 50.3 grams of aluminum bromide is my actual. And then I'll do the calculations to figure out what my theoretical was, how much I think should have been produced, and then we'll find the percentage. All right, so we're starting with, or we did start in the lab with 6 grams of aluminum. We'll need a balanced equation to do the stoichiometry, so we got aluminum reacting with bromine. Remember, bromine's one of our diatomics, so it has to be Br2. And then that's going to produce aluminum bromide. So that's an ionic compound. You need to think about the charge of aluminum. It's a +3. Charge of bromide, it's a -1. So the correct formula for aluminum bromide is AlBr3. All right. Then we go and balance it. So we need to put a 3 here, a 2 here, and a 2 here. All right. So now we can do the stoichiometry. We've got 6 grams of aluminum. We're going to change that into moles. So the molar mass of aluminum, look it up on the periodic table, it's 27 grams of aluminum for every 1 mole of aluminum. And then in the balanced equation, we want to figure out how many moles of AlBr3 are produced every time a mole of aluminum reacts. It's a 2-to-2 ratio. And then we need to add together the molar mass of aluminum bromide. So let's see, we've got 3 bromines. Each bromine has a mass of 79.9. And then we've got 1 aluminum, which has a mass of 27. So we add that up and it gives us 266.7. Okay, so we've got 266.7 grams of AlBr3 for every 1 mole of AlBr3. All right, so we do this on our calculators, check that everything's canceling out. Grams of aluminum, moles of aluminum bromide looks good. So we're going to get grams of AlBr3 at the end. And when we do that on our calculator, you get 59.3 grams of aluminum bromide. So that's my theoretical. Okay, so we've got my theoretical, my actual. The actual is what came from in the lab, or in this case, it was just given in the problem. Then the theoretical was based on the calculations that we've done. All right, so then to calculate your percent yield, we're basically seeing how close was the actual to the theoretical. So it'll be 50.3 over 59.3. And we find out that we made 84.8% of what we expected. So that's percent yield.